Hello students, welcome to BTech first year BITS course. In the last lecture, we have discussed the conservative property of electric field, and we have seen that if one unit charge is moved from one point to another, then that E dot dl along that path will be path independent. That means it depends on the initial position of the charge and the final position of the charge. And if we do the integration in the closed path, means if the unit charge returns back from that the final position to the initial position, and we have seen that the closed line integration E dot dl will be 0, right? Now today we will discuss the relation between the electric potential and electric field. Now let's first see what is electric potential. Now, so we have seen that the integral E dot dl is path independent, right? Now, if we consider a arbitrary reference point here and a unit charge is moved from here to a particular point, and the distance of that point from the origin where the charge is situated is r. So, the electric potential is actually the amount of work needed to move this unit charge from this reference point to this specific point inside this electric field without producing acceleration. Without producing any acceleration, that we have to consider, right? So, this is the minimum work done required to move this unit charge. And as the path integral is path independent, so this E dot dl is path independent. That's why we can write this electric potential is like this. Here this minus sign is coming. Why? Because this unit charge is moved from this reference point to this specific point, and you can see the movement of this charge is opposite to the direction of the electric field, right? So this is the minimum work done required to move the unit charge, and that is called the electric potential, and this is the mathematical form of the electric potential. Now, so let's discuss what is electric potential difference. Now, initially we are placing the charge here. Then, if we place the charge at P point, okay, so what will happen? Then, if we find out the potential at the B point and potential at A point, that can be written like this, right? So, minus this reference point to be E dot dl, then minus of minus, that is plus reference point to A E dot dl, and then we are changing the this integral reference. That means this is A to the reference point. That's why this negative sign is coming, and we can merge this, and this will come like minus A to B E dot dl. So this is very easy. You have already done in your 12th class how to change this arrangement of the integration limit. So we are getting the potential differences like this, minus A to B dot dl, and here you can see that this potential difference is also can be written like this. So this is actually coming from the vector calculus, that this is called the gradient of the potential. Now, what is gradient of the potential? And potential is scalar function, you know. So gradient means the maximum space rate of change of any scalar function. So when we apply gradient on potential, if we give the maximum space rate of change of the potential. Okay, so this is the definition of the potential difference in terms of the gradient operator on the potential. Okay, so we can write the A to B gradient E dot dl equal to minus A to B E dot dl. So as dl is a finite length, then we can write this electric field is actually minus gradient of E, right? So what does this mean? So this potential is basically, so whenever we are considering a point charge, and we can consider the potential is like equipotential surface. equipotential spherical surface. For a point charge, we can consider equipotential spherical surface. Means the potential at each and every point on the spherical surface is same. Now, if we take the gradient on that spherical surface, means it will give us the maximum rate of change of the potential along a particular direction, and that direction is along the electric field direction. And this minus sign is why it is coming, because here you can see that if we go from this q charge to any further point, that potential value will decrease, right? That means the if we go from q to the further point, potential value is decreasing along this radial direction, along the radial direction, and this is the direction of the electric field. So the as the potential is decreasing, that's why this is the this minus sign is coming, because gradient actually tells the maximum increase or maximum rate of change of any scalar function, maximum increase rate of increase of the scalar function. But here potential decreases if we go further. That's why this minus sign is coming. Now in the next class, I will discuss that what is the choice of this reference point to find out the electric potential. Is there any restriction in this choice of the reference point? Okay, so that we will discuss in the